Welcome to Punching Cards, the podcast about all things intelligent. I'm Dimitri Mollo.
And I am Aravind Battaje.
Aravind, you've been living in Berlin already for quite some time, right?
Not that much, but yeah, not too little either.
So I guess you know the city already quite well. I mean, at least the highlights, I guess.
Sure.
And I suppose you have passed at least a couple of times by the Brandenburger Gate.
Of course.
So, for those of you who have never been to Berlin, the Brandenburger Gate is one of the main landmarks of the city. Stands right at the core of Berlin next to the German parliament. Looks a bit like an ancient Greek gate with columns and all, but it was actually built at the end of the 18th century. Anyway, Aravind, I have a question for you.
All right, shoot.
How tall is the Brandenburger Gate?
You want me to tell you its actual height in meters?
Yep, exactly. No checking the internet or anything. Just tell me. How tall is it?
I don't know.
Well, take a guess.
Okay, 40 meters?
All right, thanks. Let me just make a note of your guess on this piece of paper.
Okay, will you tell me what this is all about?
Don't worry, just a little experiment. I'll tell you all about it in due time, but for now I need to get some more data, some more answers for this little experiment of mine. In the meantime, don't tell other people I've asked you this question.
Okay.
All right, so let me look around a little bit to find some more people to answer my question. So, all right, Leah, let's see what you think.
How many beds can you stack on top of each other?
That's your unit of measure.
Yes. Okay, let's say 40 meters high.
40 meters. Okay, great. Richard, I have a question for you that may sound somewhat weird.
I'm sure it's extremely overestimated, actually. So because I feel like I feel incredibly small when I approach it and I go through it.
Right.
50 to 60 meters.
50 to 60.
Yes.
Okay. Nico, now it's your turn.
Like I have to create like a mental picture and stack myself up. 20 meters?
20 meters. All right, Ben.
68 meters.
68 meters. All right. Luis?
30 meters.
30 meters.
Yes.
All right. So, Nick.
Okay, is like 17.5 meters.
17.5 meters. That was the most precise. Did you know this
What,
already?
Really? No, I don't know. I have no idea.
Thanks, Mark, for joining me.
35?
35 meters. All right, let me write this down. All right, let me see. I got 15 answers, counting mine.
Wait, but didn't you already know the right answer?
No, not at all. I didn't check the answer before guessing, and I resisted checking it until asking everyone about it. It wasn't easy, but it was to avoid biasing anyone.
What was your guess then?
I guessed 15 meters. You can see here, I noted it down together with the other ones.
Much lower than my guess.
Yeah, the guesses varied quite a bit actually. Some were rather low, like mine, and others very high, up to 68 meters.
I see. What now then? What's the point of all of this?
Okay, now I can tell you. Have you ever heard the expression, the wisdom of the crowds?
Yes, I have. I know about it because of an anecdote about Francis Galton. He was at a fair in England in the early 1900s, and there was a sort of competition going on. Whoever came closest to guessing the weight of a particular ox on display there would win and receive a prize. Galton looked at all the hundreds of guesses and took the average. And surprisingly, the average was very close to the right answer and was better than most of the guesses, even the ones given by cattle experts.
So the crowd, taken as a whole, did better than each single individual.
And now you want to see whether the same will work for the Brandenburger Gate?
Yep, ready? So let's first add up our 15 answers, divide by 15, and we get 33.16 meters.
All right, let's also calculate the median just in case. So it makes 35.
All right, so time to check the answer. Okay, according to the official website of the Brandenburger Gate, it is actually 26 meters tall, including the statue on the top.
Okay, our average was close, but not that close, about 7 meters too high.
That's true, but it wasn't that bad either. Out of the 15 people we asked, only 4 got closer to the answer than the average. So the crowd was still wiser, so to speak, than 9 out of 15 of us, including me.
And me. Perhaps if we had asked more people, the average would have been even closer. 15 is a rather small crowd after all.
Probably. We are definitely far from the hundreds of participants in the crowds that people have done experiments on. Okay, Aravind, next question. And don't worry, this one is easier. Do you sail?
No, and I never did.
Yeah, I never sailed either. But I did watch sailing competitions every now and then on the telly, and especially during the Olympics. In most cases, you need a crew of several people to move the boat around, each person doing different things at the right times.
Yeah, it looks like a dance.
But in that case, there is no real predefined choreography. It's something more like an improv dance. You have to respond to what the ocean is doing, what the boat is doing, what other people are doing.
And what do you think they will do? If 2 of the people decide to do the same thing at the same time and the same place, it won't work all that well. It's a tough task to solve. Steering the boat, coordinating with everyone else, reacting the right way at the right time, and all that while racing.
So if the crew is going to be successful in steering the boat around, let alone winning a race, they kind of have to work as one, each contributing a bit to controlling and steering the boat. None of them would be able to do it alone, not with those boats and not at those speeds at least.
They have to work as a team.
Which is another name for a collective.
Now I see where you're going with this. So sailing is a task that most people would agree requires quite some intelligence, I think. And in this example, it is not being solved by the behavior of any individual alone, but by the collective behavior of the whole crew. Maybe then we could say that the whole crew, as a group, is intelligent?
This example was actually inspired by ideas proposed by the anthropologist Edwin Hutchings in the mid-90s. He spent some time in a couple of West Navy ships investigating how they work. Not in the sense of how their mechanical parts work. Well, not only that at least. He suggested that crew members, together with the spatial layout of the ship, its mechanical parts, and of course all the stuff that the crews produced, like maps, codes, etc., well, that all of this together was a form of what he called distributed cognition.
The basic idea, if I'm getting this right, is that by coordinating with other people and by being in a place that is like spatially and materially organized in a certain way, we get some capacity, some skill that goes much beyond what any person could have. So a collective can, together, solve a task that requires intelligence.
Just look out of the window. The traffic down below flows so well, not because a person planned the trajectory of each car, each bus, each pedestrian. What they did was to distribute the solution of the task between motorists, traffic signs, traffic lights, white stripes on the ground, pavement separated from the road, etc., etc.
And that's very different from what we are talking about earlier, isn't it? This isn't just the wisdom of the crowds. There we each gave our answers separately without coordinating at all. You didn't let us do it.
Yeah, not much distributed cognition or collective intelligence in that case, no. While it required intelligence from each of you to give an informed guess, there was nothing over and above that.
I think it's fair to say that we were not really a collective. We were just individuals having their guesses added together and divided up to get the mean. So maybe talking about collective intelligence in this case is a bit of a stretch.
I agree, and I think that's a crucial difference between the two cases. So you would be more comfortable saying that the sailboat crew is showing collective intelligence than what happened in our little experiment?
I think so. But then, well, you give the example of the traffic on the street below, and this made me think of ants and how they also seem to have a sort of organized traffic going on, all moving along the same route towards food or whatnot. Of course, this is quite different from what we do with all our fancy signs and driving licenses and so on. But I wonder to what extent there is really a fundamental difference here. Maybe it makes sense to see what the ants do as a form of collective intelligence too.
And bees, perhaps, termites, fish schools, bird flocks.
Pedestrians in a crowded intersection, But more on all of this in a moment, after the break. I'm joined now by Solveig, also from our cluster, to talk more about collective intelligence with some experts.
Hi, Aravind. It's great to be here. Yes, in order to go deeper into this topic, we had conversations with two scientists working on collective intelligence. One of them is our own Jens Krause, a principal investigator at Science of Intelligence.
My main research interests lie in the area of collective behavior and collective intelligence, and also in the field of social networks.
And then there's Guy Theraulaz, leader of the Center for Research in Animal Cognition in Toulouse, France.
Basically, I'm a behavioral biologist and an ethologist, and what I'm trying to do is just to apply the same kind of methods to look at different phenomena in social insects, in pre-social insects, in fish schools, in flocks of birds, in human crowds, to try to shed light on the underlying mechanisms that control these phenomena.
I guess a good way to start is with the notion of collective intelligence itself. I was talking to Dimitri earlier, and our intuition is that things like the wisdom of crowds does not really count as collective intelligence, but a crew steering a boat does.
That is very interesting. But let's take a step back first. Let's look at what Jens and Guy think counts as intelligence in general.
As an experimental biologist, intelligence for me is problem solving, essentially. So I look for instances where animals are capable of solving problems, and because I normally film animals, I want to see behavior solutions. So that's how it manifests itself when I look for solutions. I will look at behavior that is capable of dealing with a particular problem.
Now, what I found really fascinating is that what Jens just said is very close to what Guy also thinks. But Guy takes a somewhat different perspective on all of this.
I have a really pragmatic way to define intelligence. It's the ability to solve problems. Of course, the problem is that the observer of a system define the kind of problem generally. So it's not entirely a definition which is centered on the organism. You also have to consider the observer. For instance, when I design an experiment where on one side I have an ant colony and on the other side I have a food source, and I connect the colony with a bridge with two different lengths, a short length and a long length, I'm creating a problem. I'm creating a setup and I'm defining a problem. But from the ant point of view, there is no problem. Still, the system is solving a problem because in the end, most of the time, the ants are able to select the shortest path.
So both of them agree that intelligence has to do with problem solving. But as Guy points out, what is a problem depends to some extent on us, a problem that we consider to require intelligence.
Exactly. And of course, what we consider to be problems is also going to shape the kinds of experiments we do.
Doesn't that make intelligence be all in the eye of the beholder, so to speak?
That's one way of seeing it. But I think we can also take the lesson to be a bit less radical. When we talk about intelligence, especially non-human animals, we have to be very aware of how we, as observers of their behavior, bring with us a lot of baggage about what a problem is for us, what solutions really are intelligence, and so on.
I liked Guy's example of the ant colony finding the shortest path to the food. I guess no individual ant has in their minds the idea that there's a problem to solve and there is no leader drawing plans on what they should do to get to the food, but the whole colony needs to find food. And by each ant doing its thing, even without anyone planning, they end up finding the shortest path. Maybe this example gives us a clue about what distinguishes collective intelligence from individual intelligence.
I think that they are solving a problem collectively because they are using interactions. Without any interactions between ants, they will not be able to find the shortest path. And this is why we are talking about collective intelligence or swarm intelligence, because most of the time, each individual is not able to find a solution.
Let's also take this other example that Jens gave, which is about a completely different species.
We looked at situations where a school of fish is confronted with a right-left decision. They can either swim to the right or to the left but one of these two choices will have a predator that is cryptic, so it's not easy to detect. And now we would expect that a single fish or a group of fish, if they detect the predator, they avoid it and they take the safe side, safe option. And indeed they do, but sometimes they don't see the predator, of course. And now we measured how much better a group gets at avoiding the predator as a function of group size. And we found that single fish were very bad at avoiding the predator because very often they didn't spot it. And as group size increased to 8 or 16 fish, the detection probability was close to 90%. So we found that groups of fish were much, much better at detecting and avoiding the predator than the single fish. And to our great surprise, they were also much faster. So they made a better decision and in half the time that a single individual did.
Here too, we have a problem, this time detecting a predator. And this problem can be better solved by the collective than by the individual.
I think that the interactions and the richness of interaction, the richness of the way interactions are integrated at the individual scales, provide groups of animals the ability to develop a rich repertoire of collective response, to different kind of situations. And I'm not talking here about learning abilities, because this may also add another complexity level to the system. And you can describe that as a manifestation of intelligence.
And sometimes the solutions to these problems are just not things that individuals can do. Only groups can deal with them.
Like steering a big ship?
Or figuring out where to swim to if you're a school of fish.
So my personal view on collective intelligence is that this is an ability to solve problems that an individual animal or human would not be able to solve in that way, or not as well. And so ultimately the group is better at something than an individual, maybe even so much better that the individual can't solve that problem at all. So that it's not just a graded response, you may even go over the threshold that for certain problems you then need a group. Other scientists have views on collective intelligence as something that emerges from multiple individuals or multiple cells in a tissue being present and interacting in a way that is only possible because it is generated in that way. So an individual per se would not be capable of creating such a solution because it's alone. It can't network itself in such a complex way. And so for them, collective intelligence is something that only collectives can generate, if you like. I mean, to give you an example, there is this nice work by Andrew Birdall. They looked at fish schools. These fish, they want to be in a darker part of the environment because that's where they feel safer. And now the group swims around, and when one individual encounters a darker area, and let's say it's an individual on the outside of the school, then this fish will swim more slowly. And if they stay together, then the outside of the school will curve around and they inevitably steer into that darker area, okay? And there you can see this kind of gradient sensing can only be done if there are many of you. A single individual can't do gradient sensing. So this is an example of a collective intelligence property that is only available to, more individuals. But I think these two views on collective intelligence are in a way connected or similar at least. So I don't think it's the difference is this great. And some people talk about swarm intelligence, others call it collective cognition or whatever, wisdom of the crowds. There are many, many different words for essentially the same thing, that in groups, problem solving becomes superior in some way.
That's so cool. I've heard people sometimes talk about superorganisms in cases like this. The idea being that we should treat the whole collective as a single organism, having needs, goals, solving problems, and so on.
The concept of superorganism is a bit controversial, and it is often used to make sense of what social insects like ants or termites or bees do.
Because this term integrates the fact that you have a complex systems, so a system of elements in which organisms that strongly interact with each other, and you observe some emergent property at the group level, which is a way, in fact, to define a superorganisms, a coherent whole, that emerge from these interactions.
Right. The interactions between these insects are so intense and determinant of the group's fate that it makes sense to see the whole ant colony, or the whole termite mound, or the whole beehive as one big organism composed of smaller ones.
Yes, they end up behaving like a whole, as Guy said. But from what I understand, there is collective intelligence even when it makes less sense to talk about superorganisms, like in schools of fish or humans steering a boat.
What makes them behave like a whole, though? I mean, there's no central planner, no boss telling each ant or termite what to do. How did they manage, nonetheless, to find food, build colonies and mounds, and defend themselves from predators? They can't even talk to each other, like we often do when we collaborate to do something.
Yeah, they don't speak, that's true, but they use other ways to coordinate. The key word here is stigmergy.
Well, stigmergy, it's a concept that was introduced by Pierre-Paul Grasset in 1959. He was working on this concept about 10 years before, because he was trying to really understand how termites coordinate their behavior to build a nest. And he had the intuition that the past activities of individuals in the environment, for instance, the material patterns or the chemical patterns that they are producing, may affect their own behavior, but also the behavior of other individuals in the colony. And from that kind of indirect interactions, some kind of coherent behavior can emerge.
And even though it's a simple mechanism, it can lead to very impressive behavior. It's somewhat close to what we also do sometimes. Think about what happens in parks and green areas where lots of people pass through. Even though normally these areas are designed with predetermined paths that people are supposed to follow in asphalt, dirt, or pebbles, after a while, you see very clearly that trails start forming in the grass. This is people taking shortcuts, finding the shortest path to their destinations.
And the more people use this shortcut, the trail gets clearer and clearer. And the clearer it gets, more and more people will notice it and use it too.
Exactly. So the behavior of each of us changes the environment a bit. And the more it changes, the more it influences other people's behaviors. So little by little, a shortcut through the lawn takes shape. Perhaps becomes the way that most people actually take, for the despair of city planners and architects. Bees, ants, termites, they all build their complicated hives, colonies, mounds a bit like this.
So basically, stigmergy, it's a kind of indirect coordination that emerge from indirect interactions between animals and some traces of their past activities in the environment. Okay, and the interesting thing is that you can create many, many complex behaviors. And we have a paper that will soon appear on termite behavior, where we found a solution, in fact, to a very old problem, which is the creation of helices, of helicoidal structure in Apicothermes nests. These nests are probably among the most complex structure ever built by animals. And inside this nest, you can find extremely complex structure, especially some kind of helicoidal staircase, that connects the different level of the nest. We have been able, with a group of Harvard, group of Mahadevan, to model the individual behavior that are involved in the creation of these kind of complex structures. And the model recreate exactly the kind of complex structure that we found in these nests, with extremely simple rules.
One of the cool applications of this research is to transfer the simple but amazingly efficient strategies of social insects to human design. Perhaps by using these principles, architects and city planners can design cities and buildings that help organize our own way of interacting with our environment in more efficient and more pleasant ways.
And without ruining the lawns with our lazy shortcuts.
Yes, there are some lessons that we can learn from the humble ants and termites.
Because architects now are looking for this kind of indirect interactions, how you can shape the collective behavior of people in a building by playing with this kind of constraints. to organize the contact, to facilitate contacts, or on the contrary, to help people to avoid to have contacts, to also self-organize the collective behavior of people inside the buildings, depending on the day, depending on the light, for instance. They can play with this kind of principles in which people interact with the structure, but also they also respond to the behavior of other people and also the light in the building. So you can play with these different variables to create a more intelligent building.
And it doesn't stop at architecture and urban planning.
Social insects to try to apply this model to different kind of problems, to solve different kind of problems, like finding the shortest path between cities, organizing the traffic into the telecommunication network, optimizing the traffic, using artificial ants to analyze in real time the traffic, and then to organize the path of data, the packets of data that are traveling on the telecommunication network.
Truly fascinating stuff. These sound like very useful insights to take from these insects. But I guess there's even more, right? We humans like to plan and all, but it also happens that we form groups somewhat spontaneously, like when we form a line in front of the cinema or try to negotiate being very close to strangers in a bus or lift or a train.
Or go to protests or demonstrations. And here there are lots of important things to try to understand and predict for very practical purposes. For instance, will the crowd become violent? If so, what should be done?
You can already see that in police manuals. There are now already chapters where they talk about de-escalating. This is still mostly anecdotal, it's mostly observational and descriptive. And I think we as natural scientists, we hold the key for predictability of such events. Of course, we need the other sciences and so on, but ultimately we are in the business, of predicting tipping points and these kind of things for complex systems. And I am convinced that also in big crowds, you see early warning signs of this kind of thing. The noise level might suddenly go up exponentially. The density might increase. There might be quite a number of early warning signs that tell us something is changing in that crowd, but we still don't know what these things are specifically linked.
For such complex kinds of phenomena, with so many different people interacting in complicated ways, we also need contributions from different areas of research in order to try and understand better what is going on and to predict when things will change in the crowd and what direction these changes may take.
Would be the outbreak of violence in large human crowds during demonstrations or other protests. And there you really need, sociologists, cognitive psychologists, collective behavior people, and physicists or computer scientists who can deal with large multi-agent systems and so on. And it probably takes all these four perspectives to really be able to explain and predict at which moment violence will break out, because that's ultimately what we want to be able to do. It's like, forecasting the eruption of a volcano in a way, we saw these things happen in our societies. The police, the security forces were taken completely by surprise. They underestimated these kind of things. They didn't, even while the drama was unfolding, they didn't see it coming to its full extent, And I think these are serious problems in our society where we currently lack predictive power.
Jens mentioned big data earlier. Doesn't it fundamentally change how research on these topics is done?
Definitely. Compared to how things were earlier, today we have many more tools to investigate collectives than before, and they're faster and much easier to use.
And the problem by that time was that we didn't have a lot of tools, in fact, to track all individuals. We do not have the same kind of tool that we have now. All these barcodes, these QR codes, all the deep learning techniques that now you can use to track individuals, to reconstruct interactions. By that time, you had to do that with the computers that we had by that time, in fact. So you had to look at the society, you had tag each individuals with small tags, and you have to do that by eyes. I remember that by that time we use a keyboard, and we had changed the key of the keyboards with the colors of the tag that corresponds to each individuals, And we have another part of the keyboard where we code the interactions, on one key that corresponds to one individual, another key that corresponds to its behavior during a 2 minutes period. And we do that every 2 minutes period. We scan the whole society. We had 4-hour observation per day, 2 hours in the morning, 2 hours in the afternoon. It was extremely painful, I can imagine. 7 days a week during 2 months. So just to give you an idea, of the working conditions that we had by that time, 30 years ago.
Let me first of all say that for me as a biologist, it has been super encouraging to see that in my field, we are probably the first generation of biologists where empirical data are not the bottleneck anymore. So I think in the past, our empirically collectible data, they were so small that biology, certainly in the behavioral sciences, was an area of storytelling. So we would observe 8 or 10 or maybe 20 individual animals, and then we would look for commonalities, and then we would tell a story that explains it. And I mean, we could do simple statistical tests, and calculate a p-value. And now we have the capability of getting data from hundreds of thousands, even millions of individuals. We can see how they respond to each other in subtle ways. And with the help of mathematical tools, we can begin to see how complex decisions arise from this. And so collecting empirical data is no longer the bottleneck for this kind of enterprise. And this has opened the gates for collaborations that biologists had never had before. I'm working a lot now, mainly even with theoretical physicists and computer scientists. And this gives me hope. I mean, that now that we are freed from the difficulty of data collection, we can maybe test some of the more exciting concepts that require enormous data sets, but at the same time, not be so naive to think just because we have more data that big data, is a concept in itself. Of course it isn't, You still need to think very carefully then of how these data are, harnessed, how networks, how the individuals are linked in there. What are the sort of algorithms of decision-making that are played on these giant networks of the data that you collected? So we are not freed of the hard thinking for new concepts. But in some cases, concepts already exist that had never been testable with small data sets. Really nice high-level concepts that are very data hungry, and then large novel data sets from decision-making and problem-solving in animals, and ideally even in the field, animals in nature, in large collectives, solving complex problems, and then physicists helping us to deal with these huge data sets, testing specific hypotheses. And my great hope is that this will provide major new insights in the field of animal cognition and also intelligent algorithms in the coming years.
But as Jens points out, we have to be very careful with big data. We shouldn't give it too much weight and neglect coming up with good theories and hypotheses. This is also something that Guy worries about, especially when this data is used with machine learning techniques like deep learning, which is all the rage now.
I think they are extremely powerful for instance, to analyze patterns, to reproduce things. The problem is that from a scientific point of view, it provides no information because it's just another way to reproduce the same kind of data. You don't have any understanding of what's happened in your system. What are the mechanisms that, in fact, control your system? It's just a way to acquire a huge amount of data and then to fit with all this weight on the neurons. The problem is that, okay, you reproduce something that closely resembles what you observe in real, but you don't have any understanding of what's happened in your system. We are scientists, we are not engineers, and as scientists, we need a deep understanding of all the mechanisms, all the interactions, and the way the element of your systems combine these interactions and give rise to the properties that you get at the collective level. Because then you can control one interaction, keeping one interaction constant. So you can have a very a much richer understanding of what's happening in your system. And I think that deep learning cannot provide these kind of things.
Yes, I agree. All this data and new methods are helpful new tools, but they do not eliminate the role of creating theories, trying out explanations, coming up with new concepts and insights. Thanks, Solveig. This was really fun.
Sure, Aravind. It was a pleasure.
I'd never have thought that the behavior of the humble ants could be a good way to design our cities, or even learn how to manage human crowds.
There is strength in numbers, as the saying goes.
And different kinds of strength, right? Wisdom of the crowds, collective intelligence, swarm intelligence, superorganisms. They all seem to have to do with the realization that bigger numbers of ants, bees, fish, humans make things possible that wouldn't be otherwise.
Right. They are variations on the same theme, but they work differently, and the kinds of phenomena that arise from them are also often quite different.
Alright, so I guess it's time to call it a day, for now at least. Next time, we will take a yet different perspective towards intelligence. We will be talking about the evolution of intelligence, how our intelligence may be different from that of other animals, and much more. Thanks for joining us today, and I hope to see you back for the next episode of Punching Cards, the podcast about all things intelligent.
And now, time for some fun facts. One of the many fascinating things about Rome is the complicated dance that starlings display every year in its skies. Thousands of birds fly in synchrony, drawing a variety of shapes, moving like waves against the typically blue Roman sky. This collective feat of the birds, which of course has little to do with aesthetics and much more with avoiding predators, has piqued the interest not only of passers-by but also of scientists, and at least one Roman Nobel laureate. Indeed, half of the 2021 Nobel Prize for Physics went to Giorgio Parisi for his work on the behavior of complex systems, and in particular, as the Nobel Committee put it, for the discovery of the interplay of disorder and fluctuations in physical system from atomic to planetary scales. Before winning the prize, one of the complex systems he studied lay somewhere between the scale of atoms and planets. It was the flocks of starlings dancing in the skies of Rome. Punching Cards, the podcast about all things intelligent, is a production of the Science of Intelligence Cluster in Berlin, part of the Excellence Initiative of the German Research Foundation. The podcast is produced, scripted, and coordinated by Aravind Battaje, Dimitri Coelho Mollo, Benjamin Lang, Nicolas Roth, Olga Shurygina, and Solveig Steinhardt. Editing by Valeria Beccattini. The music was composed and performed by Solveig Steinhardt and Dimitri Coelho Mollo, and mixed and produced by Aravind Battaje. You can find and follow our podcast on Spotify and Apple Music and all your favorite podcast platforms. For show notes, links to additional material, more information, and to contact us, visit www.scienceofintelligence.de/punchingcards or follow Science of Intelligence on Twitter.